I'm going to introduce the first speaker, who's going to set an excellent example of what we are hoping to achieve during the series of presentations. And Laurie, of course, is a distinguished colleague here at Duke, the author of two excellent books, one on experimental methods and non-air vibrations, and the other one on the interaction between vibration and buckling. And he has several of his former students who will be presenting later, who are now also very productive members of faculties across the country. Laurie?
Okay. Well, thanks. So I should just also mention that we have a portable microphone for those who prefer to kind of walk around as they make presentations. So this is my contribution. And let me just briefly explain the background to this. So, has anyone seen the video of G.I. Taylor's famous experiment on reversible fluid mechanics, where he has some cornstarch and he puts a droplet of dye into a fluid, turns one cylinder inside another, and it kind of mixes the fluid, and then he turns it the opposite way, and lo and behold, it reappears. So that's an example of a reversible system. And a colleague of mine here at Duke, Tom Witelski, who's a mathematician, wrote a paper about 10 years ago where he looked at a dynamical system where there were, with a time-dependent time-dependent potential energy function, which meant that certain equilibria exchanged stability. I'll explain what that means in a moment. But the idea being, if you have a system with perturbations that directly affects the stability of equilibrium, you can do interesting things in terms of enhancing, domains of attraction and so on. And Tom, being a mathematician, he could solve these things using asymptotic methods, and he was most interested in first-order dynamical systems. We think of those as being an overdamped system. Anyway, in his paper, I think it was in Physics Letters about 10 years ago, he said, a motivational example might be a potential energy function with a double whirl that rotated, right? So minima become maxima and vice versa. And that kind of interested me, and I thought, well, maybe we could build a mechanical analog of that. So I've been working with Tom and Richard. Where's Richard? One of my graduate students at the back there. And this is a design so imagine a ball, or don't imagine, look, a ball bearing that oscillates within a track, and that track is completely confined. So here we have two minima and a maximum. We're all familiar with this from Duffy's equation, basically. So if you shake this from side to side, you can get various interesting behavior. If you turn this upside down, then the central equilibrium is now stable, and the two on the sides are unstable. So that's kind of like a pendulum, somewhat. So I thought, well, let's extend this idea by having a complete, I'm not sure what you might call this, maybe a peanut shape, that then rotates as it's shaken from side to side. All right, so the motion, there's lateral forcing and tilting, and it doesn't have to be at the same frequency, it's just convenient mechanically to do that. So you can see that these two equilibrium points there and there are stable when we're on this side, and when it tilts to the other side, the isolated equilibrium, the other equilibrium becomes stable. So let's look at what we built in the lab. So here we have a small ball bearing that oscillates what you can barely see inside this grooved track. And we prescribe this shape exactly using a milling machine, so from an equation. And then there's a camera that's mounted perpendicular to the plane. So this camera, relatively high-speed digital camera, tracks the motion of the ball. All right, so it's kind of an interesting system. That's why I call it reversible equilibrium, because of this exchange of stability. Okay, so that really is described here. This is the equation of motion. Now, it's interesting. You can describe this in terms of arc length coordinates. or Cartesian, and you can go from one to the other, and there are certain nasty issues associated with that. But in general, you think of S as being an arc length coordinate, and S dot, the rate of change of S, is the velocity as you go around. And then, of course, it is a three-dimensional phase space because we are forcing systems. There's a forcing phase issue. So this is the equation of motion where x and y are known functions. I mean, that's really what was input to the milling machine to get this shape. And here's a typical experimental time series. And so you can see the ball does this kind of Duffin-like double whirl behavior where it oscillates between and about the two equilibria. You can change the frequency and the force-in amplitude quite conveniently using the Scotch yoke. And you can get different types of behavior. So here's some typical results. And this is, hot off the press, in fact, just a couple of weeks, some of this. Now, in terms of a bifurcation diagram, one convenient way to couch this is in terms of a spectrogram. And I guess you're probably familiar with this. This is where we're looking at the spectral content, the frequency content, as a function of a control parameter, which in this case is force and period. And we're looking at the frequency content, and then the third dimension, the color contours, is the power, if you like. So you can think of these as just FFTs all stacked up together. So where you get a single stripe, that's basically harmonic motion, although there are some higher harmonics, so it's more, it's not quite as simple as simple harmonic motion. And as you change the parameter, you can go into this broad band where the behavior becomes complicated. Possibly chaotic, or we suspect chaotic. So this is numerical simulation of that equation of motion that I just showed. And this is this experimental analog. So again, you get this broad min, where the motion becomes complicated. Doesn't line up terribly well, but there's always issues with damping and so on, and we're looking for a qualitative similarity. So here are some specific results. So these are phase trajectories plotted in x. We could plot y and y dot or s and s dot. So this is the trajectory that of the ball in terms of an x projection. And this is numerical simulation. And this is what we get experimentally. So this is what the camera is seeing in terms of a pixelated image and projected onto x. This is a Poincaré section, theoretical, numerical simulation, and experimental. So there is some pretty good similarity between these two. In fact, I think we even have some better results, don't we, Richard, than that? So I'm not entirely sure that this is the most recent result. Is that a 3D plot?
Yeah.
I really can't see from here. Anyway, so there is clearly structure here. And what I would say is one thing so this is really work in progress. It seems as though there might be two attractors superimposed. And so one depends on when the motion is, the ball is oscillating about the double whirl configuration, but then that's switching to where the motion is about the single whirl. And it's almost as if there's two strange attractors superimposed, at least in some of the other results. So the issues we're just grappling with at the moment is if you have a non-tilting system like this, if this just went backwards and forwards, it's basically Duffin's equation. Okay, the ball is always going to be oscillating about in between those two equilibrium points. If you then start tilting, you can imagine tilting about a non-zero mean. In other words, you can imagine this angle going, say, between, 60 and 30. So that, yes, it's always stable equilibrium, unstable, stable, but the strength of that attraction for those equilibrium points changes, right? Because it's getting shallower and deeper. But the sign, if you like, the eigenvalues, the sign of the eigenvalues don't change. And then the extreme, which is what we're most interested in, is this third one, tilting about a zero mean. So that's where this thing actually goes from, say, minus 60 to plus 60, like in the video. And that's where you get the exchange of stability of the equilibrium points. So that's where this project is at, and the ability to manipulate these equilibrium points and perhaps influence the global stability and basins of attraction is the thing that we're going to do next. So that's my little contribution, and I'll be happy to answer questions if you have any.
Alex, Laurie, what was the ratio between the frequencies?
They're actually the same.
1 to 1.
Yeah. That was just convenient. The actual form of the tilting doesn't matter as long as there's some time perturbation of the equilibrium points. It doesn't. The ratio between those frequencies is not important. I mean, it can certainly change the behavior, but to display the certain behavior that Tom Wojtelski, wants us to display mechanically, that ratio isn't important.
Another question? Bill?
I can't resist, Lori. It's only rock and roll, but I like it.
All right.
All right. Well, we can continue that conversation at the break.